All right, let's talk about magnetism. And to give some evidence that magnetic fields are more than just make-believe.
We had a much more three-dimensional display tool, piece of equipment. However, neither Assassin nor I can find it.
Not sure, okay. All right, so we have just, these are little flecks of iron that are inside some sort of gelatinous form. And I have a magnet. When I put a magnet onto it, oh, this is not as nice a display as the other one. You notice that we do have filings being attracted to it. If I had half the number of filings, that would work really nicely. You can start to see some alignment going on with the other ones. You can see these lines sort of coming in like this. Yeah, it's really tough to see unless you're actually looking for it. So perhaps this one will work better. Well, that was disappointing. All right, so we have some random, they're just little pieces of, I assume, iron. Ah, that's part of the problem. That's an incredibly weak magnet. Let's see if this works any better. And if you'll notice, we have these lines here. Basically, they have oriented themselves along the direction of the magnetic field. So we have a line coming out like this, and it sort of flows around into here. And the same on the other side, we get the reorienting. So you have some sort of a sense of, there seems to be something going on there. Now, when we do our nice drawings in class, they're coming in or out of the ends. Now, which is the north end and which is the south end, you can't tell from this, but they are polarized. But you'll notice that this is pointing like that as opposed to like this, which it would if we were drawing this in class on the board. If I take this magnet and I break it in half, we still have a magnet. It is weaker than it was before. You can see that some of these ones that are a little bit farther away don't seem to be as affected the farther away we get. And with this magnet, we'll try this other one again. See if it actually shows up. So we get some swirling patterns there. You can definitely see some lines coming along like this, or reorienting. Much better display than that. So it gives some credence to this idea that magnetic fields do exist. It is more than just some mathematical convenience. Sorry, I think it's a cool display. Although you're not voicing it, I assume in your head you're all going, ooh.
Well, I know which end's the north end now. I assume this is labeled correctly. Let's see, where's it gonna block Ethan's view? The glass left off. We had this idea that there's a force on a moving charge, V equals Q, V cross V. I guess technically it doesn't have to be in parentheses, but. Or that is on a moving charge, so a charge Q at some velocity V exposed to a magnetic field P. And that's also going to be I L cross B. I believe we derived. And that is for the force on a current. So let me present to you another equation and have you speculate what it is telling us. So let's go with this one right here. We'll just do magnitude. Equals I1, I2, L over 2IR. Based upon the letters that are being used, there's no bizarre bizarre symbols that we have not used before, so.
I kind of want to say solenoid, like the wire wrapped around a tube kind of thing.
Why solenoid?
When I see pi, I just think of circles.
Okay.
I don't know why there would be two eyes, but
Yeah, that's the solenoid is something different, but
I think it has something to do with two, and then maybe two currents coming into contact with each other.
like this, where the current splits and then the two currents come into contact with each other. Is that what you were thinking?
More like a monster or another monster clashing.
Two currents coming towards each other.
Yes. And then the length between their crash. And then the mu sub naught of their crash.
Yeah. What is mu sub naught? Feel free to look.
Permeability of free space.
Say it again.
Permeability of free space.
Yep. It is a constant. All right, so the two I's, let's just start with that. The two I's.
Oh, did I have something?
Current.
We have two currents, okay?
We had an equation where at the very beginning with like Q1, Q2. And
Yep.
And can I use like, is this like just that, but it was KE Q1, Q2 over R. Just like that.
That's the electric potential energy.
Yep.
so what I'm thinking is the free space thing is you have two currents going some distance over, could it be like a ring kind of thing? I'm just thinking of problems we had with circles,
Okay.
which was the one with like the ring on the inside. It was like current on the inside of a ring.
All right. Let me sort of parse this apart. One, this has something to do with magnetism. This is a magnetic force. Now, first off, I didn't put the subscript here. I do have a subscript, I believe, in the list of equations. There's a subscript. I do float back and forth between the subscript that I use for magnetism. Sometimes I tend to use B the most, but sometimes I'll just use M for magnetic or B for magnetic. Oh, did I ask last time about why B for magnetic field? The guy who was writing this down the first time, the one who set the standard, had a couple different vectors. And the first one he labeled A, the next one he labeled B, the next one was C, and so on. So for some reason B stuck. There is a what's called a vector potential, which is the A. All right, it does involve two currents. A circle is involved, but be careful about the circle is not the geometry of the wires themselves. The circle is the geometry of the magnetic field. Because we talked about before that if I have a current flowing straight back towards Giselle, that the magnetic field that's produced, right hand rule, thumb points in the direction of the current flow, and the fingers go in the direction of the magnetic field. So their magnetic field lines are going in a circle. So that's where this part comes in.
So is it just two magnetic fields hitting each other? Or interacting with each other?
It probably better wording, it is the magnetic field that if I have two parallel currents,
Oh, them combining, sort of?
it is the effect that one has on the other. And L is the length of the parallel part. So just do a quick plug and chug here. I have two currents like this. Let's make this 3 amps. Let's do something. Sure, why not? 3 amps and 5 amps. They each produce a magnetic field. The force from the magnetic field is demonstrated by this. So if this is I1 and this is I2, then the force, the magnetic force on 1 from 2 is going to be, what's the force on 1 times that length right there across whatever the magnetic field is that is produced by 2. So current 2 is producing a magnetic field which is influencing 1.
You can do that vice versa.
Yes. I think it was one of that multiple choice test of which one exerts more force on the other. Does 1 have more force or 2 have more force exerted on it?
It's just a quick question, Matt.
Okay.
Is that included in one of the 4 tests, that concept test that we're gonna take?
Yeah.
Okay, so we'll have like 3 normal tests and then the concept one?
Yes.
Okay.
Normal. What's normal?
Not physics.
Oh, super normal. Uber normal.
Abnormally normal.
So on Friday we had this all teams meeting.
Yeah.
Nothing but excitement. But they had a student that they were interviewing, and he said his favorite subject was physics, and some people seem to think that was an odd statement to make.
My dad said that.
He's a physics guy.
No, he's a history teacher and he told me that because he thought it was surprising too.
Well, as a physicist, as a budding physicist, if you hear someone, especially family, say something like that, just look at them and just go, makes sense a lot. And walk away.
Yeah.
All right, so which wire has more force acting on it?
The smaller one?
What?
The one plus current,
That why?
because the magnetic field of the one with more current is greater than the one with less current.
Any other opinions? Or are you going,
Absolutely.
Ethan, I agree with you. Pardon?
I don't know if it makes sense, but they would be the same.
Why?
Because they're both acting on each other. And so they kind of I'm just gonna say for easiness, they just add together. And so they would both be the same one.
Same amount of force.
Yeah.
Yeah,
Do
like,
you want to give a reason why?
wouldn't it be like, because whatever it's multiplication will lead to the same thing, so when you do it in the vice versa, you're multiplying the same,
Okay, yeah, that is true. It is the same. There's a shorter answer to why it's called Newton's third law.
whatever force is acting on something will give an equal opposite force.
Yes. So if this is my equation here, if I flip my currents, it doesn't change anything. Yeah, this has less current flowing through it, so you would think less force based on that equation, but there's a greater magnetic field coming from this. This has more current, and that produces less magnetic field, but it bounces out. The one reason I'm doing this is that when I get to that last test and students start panicking, they just seem to grab any old equation that's there in the front, and I'd like you to just take a moment and stop and think of, does this equation make sense? And so being able to look at it and go, all right, in order for this to work, I need to have two currents. All right, how do I have two currents? Well, I got two wires running. Now, there is a leak between here and here. No, actually, those are the same. There is a leak between here and here, or there and here. So we'll sort of fill in that gap. I know that U has to show up somewhere. If a magnetic field, so let's say I have a current coming right at us, and I got a magnetic field that is flowing around like this, I know that the farther I am away from the current, the weaker the magnetic field, so whatever I'm doing, if that distance there is R is on the bottom, it is circular, so 2 pi R. And, well, it has something to do with the current. So the greater the current, the greater the magnetic field. And, you know, it's a magnetic field, so let's just, what the heck, let's throw mu sub naught into it.
Now, if you're, I don't even know if this makes sense, but if that field is going through something, would it be something other than mu sub 0?
Correct. Yes.
Okay.
And at some point, we'll do an experiment where you'll notice that if you put an iron core into it, you can increase the magnetic field. So when you see this equation, you get the 2 pi r's, you get the circumference, as Jack was pointing out earlier, that this deals with the size of the magnetic field. Now I'm going to sort of backpedal here. Or reverse engineer something. If I multiply both sides by 2 pi r, so I get mu sub naught, right inside, maybe. Mu sub naught times I is equal to B times 2 pi r.
Maybe the meme of this class is that which color will it want to do today?
Feels like a yellow day. It's sometimes right. And 2 pi r we know is the circumference of a circle. So that's equal to B times, we'll just put a C for circumference. It's mu naught times I. As a matter of fact, you get a circumference by just basically adding up lengths all the way around a circle. You know, you get these tiny, from a calculus point of view, you add up an infinite number of infinitesimally small little bits of length. So it's the sum of, well, actually I put D on the outside, but we'll leave it there, times delta L. And I go one step further here, since the magnetic field is going in the circle, as drawn over there. As the magnetic field is drawn in the circle, the magnetic field is going in the direction of, well, my length here. So I can change this into the sum of B dot delta L. And that's equal to mu sub naught times the current that's actually enclosed in that circle. E and C for enclosed. This is known as Ampere's law.
You said the subscript for I was closed?
Enclosed. When we were doing Gauss's law of electricity, and we were looking at electric flux. We looked at the charge that was enclosed. This is sort of the analog of it. Oop, I do need to add one other thing here. We are talking about an enclosed loop. We're talking about an entire circle here, so I'm just gonna put a little circle right there to indicate we're doing it over an entire enclosed circle. This does not work over just a line that's weaving off into space. So if I add up all of my electric field times my areas over an entire surface, that's gonna be equal to the charge enclosed over epsilon sub 9. If I did something similar with a magnetic field, well, because there is, for every north there is a south, that if I take an enclosed area, I have just as many field lines going in as out. This is equal to 0. And we now have B dot delta L is equal to mu naught times an enclosed current. Now the reason I bring these up here is I think I've mentioned Maxwell's equations before. These are part of, there's one equation and part of one equation is still missing, but this is where we are in terms of Maxwell's equations.
So, how did we go from change in A to change in L equals use of non I?
It's